Good morning, everybody. Boy, we're kind of quiet this morning. Have we already hit the mid-semester doldrums where everybody's just tired and beaten up? We're only week, what, 6? 7? We need to wait till week 9. That's the halfway point. You got to keep going, right? After week 9, you can look all, sad and all that stuff. All right. Today, we are going to finish up chapter 6, maybe start chapter 7. A little bit ahead, so maybe I'll give you some hints on the homework. We'll see where this takes us, right? But we need to do one more example from chapter 6 dealing with friction, and it's the bank term. Before I do that, tomorrow's lab is lab number 5, right? We did 6 last week, so we get to do 5 this week. And we're going to be doing connected objects in lab and figuring out all the physics there. Luckily, no friction. We'll talk about that tomorrow. All right, so we're going to do the banked turn. Now, I had to include that picture, right? Like, come on. When you search the internet for banked turn and you come up with a bus that looks like it's leaning at 45 degrees, right? Okay, as it rounds this. This apparently is at the Mercedes-Benz test facility, right? They're testing the stability of the bus. Dang. How does the bus stay up? Like, why isn't this bus falling over? Friction, normal forces. We're going to dive into this, right? We're going to try and figure out what's going on here. But if that bus were like stopped and just sort of parked on a hill like that, what would happen? It totally would fall over, right? Okay. So there's something to this forward motion and all that kind of stuff that we need to analyze. This is a more typical picture right here with this car. Now, banked turns are something that's pretty common here in the West, not so common in the East. In the East Coast, where all of the roads were developed in the horse and buggy era, there really wasn't a need for banked turns. As roads got newer or got replaced, they would have these banked turns. And there's a reason for that banking. It's a safety thing when it comes to taking a turn at speed. So we're going to investigate that and see all the forces that are involved and try to pull off a problem that really is three-dimensional. We've got left and right, we've got up and down, and then we sort of have in and out. We're going to try and tackle all of that with a two-dimensional picture. But before I do that, I have to show you this. This was something that a student sent me. This was after the pandemic, but the student was from India. And he's like, Mr. Balogh, you have to see this. So this is what he sent me. Yeah, I'm going to turn down the volume. People paid to come and watch people do this. Humans will pay for anything, right? Cage of death, maybe, yeah, something like that. Death was in the word, right? Which I thought was, very appropriate. So let's see if we can't sort of physics out what's going on here and why these cars are staying on the wall like they do. All right, so let's see. Just about everything in these last 2 chapters have started with a hill, right? So we're going to draw the hill, but the hill's going to be like it's going to be a cross section of this banked turn. Let me see if I can't try to explain this to you. Okay. It figured it out. Okay. So I'm gonna put my car on here, and I'm about to erase what I'm about to draw. But what we are looking at is the back end of the car. So like here's the trunk, right? And there's the brake lights, okay? And the back window, okay, of this car. That was really, really bad, right? Okay. But like this car is driving into the screen. So I haven't, like, if this were a top view, right? If I were looking at like a drone's eye view, okay, we'd have the turn of the road, and we'd have the car, and the car would be moving forward like that, right? But what I've done is I've like kind of cut a section out of the hill, the turn, okay, and the car itself is driving into the screen, okay? This forward arrow I've got right here, like the motor force on the car from the drone's eye view, I can't really draw on this side view because I can't draw an arrow that's going into the page, right? If we slammed the brakes on this car, right, the braking force would be coming out of the page. Again, I can't, it's a two-dimensional surface, right? There's not much I can do about drawing those vectors, okay? So, but the reason we are going to do that is because even though the car needs, the car needs some sort of forward, motor or propulsion system, right? We're going to keep this car going around the turn at constant speed. So as far as like the forward propulsion and the braking, what do we know about those two forces if we're keeping the car at constant speed? What does constant speed imply for the acceleration? It's 0. And so if the acceleration is 0, as far as the motor and the brakes are concerned, what is the net force? It's also 0. The net force is 0 along the direction of like propulsion and braking, right? Okay. Again, and we know it's vital that there is some speed v going on here, right? But we're going to keep that speed constant, which means the acceleration in that direction, that dimension, is 0. Okay. And that's what lets us draw this side view and not worry about the propulsion and the braking forces, okay, going in or out of the screen. They balance out, they go to 0, nothing interesting happening there, okay? Turns out all the interesting physics is happening in this side view, cutaway view. So what way is like the car turning? Well, it's on this banked turn. From the top view, we've got a turn to the right, okay? So the circular path that this car makes is like a horizontal circle, okay? The car is turning, going around this banked turn in a completely flat horizontal circle. In other words, kind of the way I've drawn it, you might suspect that it's kind of like at a tilted circle, but it's not. It's in a completely flat circle, right? As it goes around, right, the track, it's just going to look like it's kind of going to go back and forth in front of our eyes, okay? So as long as we realize that the plane of the circle is horizontal, right, we can do this. Okay, so let's name some forces that are acting on this car. And to name forces, we need objects. So name an object that's pushing or pulling on the car as it goes around the bank turn. Okay, the earth. And we know that that one is called the weight, and Mr. Balogh likes to call it m times g because that's what weight is. All right, what else? Normal force coming from the surface of contact, and it's normal because it's perpendicular. So again, like, these aren't too surprising, right? Anything else? Friction. Is friction required for something to be going in a circle? Well, I'm sorry, let me back up with that question. In order for a car, right, to execute a turn, is friction required? Yes, right, okay? So the question now is, what direction does that friction point? Now, first of all, is it static or kinetic friction? It better be static, because if it isn't static, the car is doing what? It's like sliding or skidding, right? And it's hard to stay in a turn if you're skidding all over the place, right? So we know that it's static friction. What direction is that static friction pointing? Is the car accelerating? Yes. Why is the car accelerating? Changing direction, right? So because it's turning in a circle, we know that the car is accelerating. What direction does that acceleration have to point? Towards the center of the turn. What direction is the center of the turn? Remember, the circular path that this car is making as it goes around the turn or goes around the track is completely horizontal, right? Car isn't like turning into the ground or like it's not doing weird things like that, right? It's just doing a horizontal circle, okay? It just happens to be doing it on a banked surface, okay? So this acceleration has to be directed perfectly horizontally to the right. There is a component of force that's kind of pointing in that direction, isn't there? Now, is the normal force kind of pointing in that direction? Yeah. Is the gravity pointing at all in that direction? No. But we know that there's got to be friction. Now, is there friction that's like letting the car go forward along the turn? Yeah, that's not the friction I'm really talking about, okay? So granted, like, again, from a top view. By the way, in this top view picture down here, which way would the normal force be drawn? Be like kind of coming out at us a little bit, right? Sort of at an angle, a little bit to the side, right? But like, that's kind of the idea there, right? So there is like a static friction that is helping to propel the car forward. I called it the motor force, right? I mean, the motor isn't pulling the car forward. The motor's attached to the wheels are on the ground, wheels on the bus go round and round, and the car goes forward, right? So we do know that there's like a friction sort of acting along the in-out direction of our page. But there's also a friction that's keeping the car in the turn. And so back to my question, which direction is that friction pointed? Is it pointed towards the center of the turn or towards the outside of the turn? It's not towards the outside. The car wants to go in a straight line, doesn't it? And again, that fictitious force, that centrifugal force, which doesn't exist, and all the engineers are going to tell you it does, okay? But they can't ever name the object that causes it, right? The force is actually directed towards the center of the circle, the centripetal force. Now, the centripetal force is just a different name for something that is already there, right? A real force is being caused by a real object. We can call it the centripetal force, but it also happens to be the frictional force, okay? And so from this sort of top view, we know that there needs to be a frictional force pointing towards the center of the circle. The friction between the road and the car is what holds it in the turn. But from our side view, which way does it go? Like, we know it points towards the center, but like, it could go like that, right? Or it could go like that. It definitely does not do that, right? Or that, because those would be towards the outside, right? And we need something that's pulling us towards the inside. So where is it? What do we know about like the force of friction compared to the normal force? They're always perpendicular to each other, right? The normal force is perpendicular to the surface of contact, and friction happens in the plane of contact, right? The plane of contact is this tilted hill. So that tells me that the frictional force has to be directed down like that. And of course, the natural question here is, Mr. Balogh, how could I possibly have known that? And I keep saying it over and over again. Knowing is how you know stuff. Now you know. I've told you, right? This is the way it is. How did I find out? My teacher told me. I wasn't born knowing, right? Okay. And how did they found out because engineers went out and figured this stuff out, right? Physicists measured and studied and looked at it, right? And through empirical data, they figured it out and they hand that knowledge on and we go, okay, that's the way it is. All right. So now you know. Banked turns, this is what the forces are going to look like. But now, oh, geez. Does anybody see the problem that's developing? Too early on a Tuesday morning, huh? What's the writing on the wall? What's the existential dread that's starting to form? Coordinate system and components of forces, right? Because what was the rule that we always follow in here as far as like a positive direction? We always put a positive direction which way? With the acceleration, right? So if I follow that rule of thumb, and we are going to, we're not going to break that one, okay? That means that I would make like positive x be perfectly to the right, horizontally to the right, which means positive y has to be either up or down, so I'll just make it up. And some of you are like, oh, glory, we're finally back to regular coordinate. No, this is bad. This is terrible, right? Why is this so bad? Now we have to find components of the normal force and the friction. Do we need to find components of gravity this time? No, it's already lined up, right? It's along the negative y-axis, isn't it? But now we've got to go, this is so bad. But we're brave and stupid. And we will have the hubris to say that we can figure this out. So there's my coordinate system. Like I said, I like to draw that sort of dotted, faint lines there right on where my forces are so that I can keep track of what I'm doing and what the components have to be and all that kind of stuff. Which one do you want to do first? The friction or the normal force? Friction? All right, let's do friction first. We need to figure out angles. And we don't have, like, we're used to like having our coordinate system kind of down like this. We go, oh, I would just know that, right? Okay, all right, so this means we need to do a little bit of geometry. There's a rule in geometry that says if you have like two lines that are parallel to each other and then you have another line that sort of goes diagonally to them, that the alternate interior angles will be equal to each other. Okay? I'm going to take advantage of that rule to figure out that that's the angle right there. Because I've got two horizontal lines, right? And then like these lines are like parallel. They're kind of offset from each other, but that doesn't break the rule, okay? So that means this angle and this angle have to be the same. So you can either like try to go figure that out or just trust me, okay, that happens to be the case. Okay, so we got that angle. Does that mean, okay, so what does that mean? That means if I go to find the components of the friction, one of them will be pointing to the right and the other one will be pointing down. I know it has to go to the right and down because friction is pointing to the right and down, right? The x component, sine or cosine? Why is it cosine? Touching the angle. All right. So there we go. Got those. Okay. Normal force. Oh, jeez. Okay. So normal force points positive y. Come back. Positive y. And then also there's a component that's pointing in the positive x. Sorry if my drawing is becoming very sloppy now, right? But again, we need an angle, don't we? Need an angle up there. So I got to do a little bit more geometry. Lucky for me, there's a little bit of geometry I can take advantage of here. I've got like this coordinate system like this. I have an angle that's sitting right here that I know, right? And I've got two things that are at 90 degrees to each other. So what does the angle in here have to be? That has to be 90 minus theta. But what I'm going for is the angle that's sitting in here. And this happens to be a 90-degree angle. So what is this angle? Yeah, it's 90 minus theta. It's 90 minus 90 minus theta. Or it's theta. Okay? So again, going fast here on the geometry, you do it once and you realize, oh, okay, now I know what these angles are, right? And forever after, you really don't have to think. I just should do that one in purple. Stay consistent with my colors. Okay, so that, I didn't really prove it to you, but take my word for it. That happens to be theta as well. So the x component of the normal force, is it touching that angle? No. So what are we going to use? N sine theta. And then the y component, is it touching the angle? Yep. So n cosine theta. Whoa! Mr. Balogh, why are you doing this to me so early in the morning? It's not me, it's the universe and Mr. Newton. Dare I remind you that you did sign up for this class? Okay. X and Y. We only got one object, that's good. X and Y start the same way, right? MA equals MA equals. One of these is X, one of these is Y. What do we know about the acceleration in the Y direction? There is none. Why isn't there any? We made sure, right, that only one of our directions, X or Y, points in the same direction as the acceleration. So, since our acceleration only lines up along the x-axis, I know that my other direction, the acceleration, has to be 0. That makes this equation easier. All right, now I've got MA equals, I can start writing down all of my forces, right? How many x direction forces are there? We're looking along this line right here, right? How many have we got? Looks like 2. Looks like we got an n sine theta and an f cosine theta, right? And what direction are they pointed? Positive or negative? They're both positive. Interesting. All right. In the y direction, so again, now we're looking along my y-axis. How many forces does it look like we've got there? I see 3. N cosine, F sine, and mg, right? It's easy to lose, isn't it? Sometimes I put check marks on the forces that I have already put in my lists, right? Just to make sure I've got all of them. So it's N cosine theta, F sine theta, and mg. I'm concentrating on getting my forces down first. Now I'll go back and get the directions. N cosine theta, which way does it point? Positive or negative? That's a positive one. F sine, negative. Mg, also negative. All right, so assuming I've gotten my equations written down correctly, right? There's several things that we can do and solve for and try to figure out here, okay? Generally, the thing that we're after is how fast can a car go and safely maintain this turn? So what's going to determine whether or not the car can safely stay in the turn? What do you think? Just like based on the sort of equations and forces we've got in the problem, what are some things that might determine how fast this car can be going and not fly off the road? The amount of friction, right? Like the strength of friction. And what's going to determine the strength of friction? Normal force is going to do it. and the coefficient. What are you guys doing? What are you guys thinking of? Yeah, I didn't do the dad joke. I didn't do the pun. It was in your own brains. Okay, so that force of friction is going to be determined by the coefficient, and that magic number is all about like how rough the surface is, how bald the tires are. Like there's lots of nitty-gritty materials information that could go into that, but the coefficient is the coefficient for a given situation. All right, so coefficient, and then the amount of normal force, right? Like just how strong the normal force is, which usually has something to do with like the weight of the car, and if it's a high performance vehicle, maybe there's downforce because of the car's shape and aerodynamics. That will affect the normal force. All right. So in terms of automobile safety, we know it has to do with friction. We have to know it deals with normal force. But if all we've got, right, is the angle and the coefficient, right? How do we determine this velocity? And I'm talking velocity. I don't see any velocity in any of my equations. Where's it hiding? It's in the acceleration, right? Because this is the acceleration for something that's going around in a circle, right? And centripetal acceleration is equal to the speed squared divided by the radius of the turn. So by getting all of this together, it looks like I might be able to get rid of like the friction, right? I can get rid of F, right? Because I know it's equal to mu times n. And then I can get rid of n because I see it in two different places. Let's see where the math takes us, right? Let's fool around with this. This is a bit of a chess game, a bit of a puzzle, right? But let's see if we can't like get some stuff to come together. So let's see here. I'm gonna start with the y equation right here. Let's take this one down here. 0 equals n cosine theta minus, all right, what can I do in place of f? I can do mu times n sine theta minus mg, right? Let's move mg over to the other side of the equal sign, which makes it positive, right? And then I've got two terms that have the normal force in it, right? So what can I do with the normal force? Factor it out, right? Get it just one of them. So this is cosine theta minus mu sine theta. And so that means that my normal force, I now found out what my normal force is going to be. It's going to be mg divided by cosine theta minus mu sine theta, right? That cosine theta minus mu sine theta is just a big number, whatever it is. Divide both sides by it. We got, okay, so that's what my normal force is going to be, right? Oh boy. So that normal force can now go here and there. What am I going to put in the place of f? Mu times n, right? Okay, so let's bring that down over here and see where we get. This is mv squared over r. That's me substituting in the definition for centripetal acceleration. I then stick in my normal force. It's going to get ugly. Mg all over cosine theta minus mu sine theta times the sine theta, which was there to begin with, right? N times sine theta, plus mu times n again, mg over cosine theta minus mu sine theta times cosine theta. Ah! Is there any hope at redemption here? Is there anything I can like simplify? Usually when I ask that question, I'm like, is there anything I can get rid of? I can get rid of m. Why can I get rid of m? It's not just on both sides of the equation. It's in every term on both sides of the equation, right? So if I divide both sides by m, I will wipe that one out. Okay. Let's solve for v. Since that's kind of what we were after. V squared. I got to move the r over. So it's going to be r times a big mess here. Looks like I've got a g and a g, right? So I can pull that out. That's a common factor. Left then with sine theta plus mu cosine theta on the top. And then it looks like I've got a common denominator of cosine theta minus mu sine theta. Yep. And then to get v, what do I do with this whole thing? Square root it, right? So I'm going to be annoying and do some whiteboard iPad math there. Okay. Oh my goodness. What the heck? What the heck is this thing? I missed a G. Oh, there's the G's in there. Okay. That, that right there, assuming I've done all my math correctly, is the equation for the speed at which a car can safely navigate a banked turn. So let's ask some questions, okay? First of all, this is the maximum speed. Any faster than this means that we are going to exceed static friction's ability to keep the tires on the road. And so going faster than this speed is no bueno. Is there a speed that we can take this turn safely if friction were to completely disappear? In other words, let's say the car hits an icy patch on this banked turn up here in the mountains, right? Got some snow, got some moisture. Overnight it freezes. Car comes along. They're driving along. All of a sudden they hit an icy patch. No more friction, right? Like it's just gone. Like it becomes kinetic friction. It's just smooth, right? What does that mean in this equation? What thing goes to zero in this equation in that context? Gravity goes to zero? No. Does the radius go to zero? No. Radius of the turn is just how, tight the turn is. What's the friction thing? It's the mu, isn't it? And for a frictionless surface, what is mu? Zero. Okay. So in our what ifs, right? If mu goes to zero, right? If we hit an icy patch, okay? Then what is our v going to be? Well, it's going to be the square root of r times g times the sine of theta, and the mu cosine theta goes away, right? Divided by cosine theta, because the mu sine theta goes away, right? What's sine over cosine? So for a given angle, not a zero angle, is there a speed that a car could stay in the turn, even if the friction goes to zero? Yeah, it's right there. It's RG tangent of whatever the angle is, right? Need a certain radius of turn, be on a certain planet, and have an angle. What happens if the road is flat? What if there's no bank? In other words, what happens when we stick an angle of 0 into this? What's the tangent of 0? It's 0, okay? So that means there is no speed at which a perfectly flat turn, right, can be safely navigated if there is no friction. So let's kind of upend that, okay, and say, okay, well, if the angle is 0, right? If our angle is 0, then for a flat turn, what speed is safe? Well, that's going to be the square root r times g, right? What's the sign of 0? 0, right? So I end up with a mu times 1, don't I? Because cosine of 0 is 1. Okay. And then on the bottom, right, cosine of 0 is 1 minus, and then what's sine of 0? Still 0 times mu is still 0, right? So I end up with a bunch of numbers. What is this? This is the square root of rug. If you rearrange your stuff. Anyway, right? So is there, for a flat turn, right? Is there a maximum safe speed? Yes. Okay. That speed gets bigger if the radius gets bigger. So like the bigger your turn, if it's not real tight, okay, then we can go faster. Okay. If we're on some planet that has a lot more gravity on it, right, we can go faster. But critically, what do we need if we want to go faster around a turn? We need more friction, right? Okay. And this is what the race car companies know, right? To make your car go faster, zoom, zoom around the track, you need as much friction as you possibly can get. They play around a little bit with this idea that they can make gravity bigger. They don't, okay? Their cars actually weigh very little. But if you aerodynamically design the car so that it like gets sucked onto the road surface, okay? Like kind of like an airplane wing upside down, okay? It gets pushed down onto the road surface. Well, if the car's pushing down on the road surface, what does the road surface do? Pushes back. And what do we call that force? The normal force, right? So there's other ways to increase your normal force other than just your weight pulling down. In a normal everyday vehicle that we drive, right, the aerodynamics are not sufficient, okay? And for all of those cars I see with spoilers on the back, you're really not going fast enough, I hope, to actually have it be of any effect. So, I mean, if I take a step back here, dang, that looks horrible from back here, right? It's just awful. There is so much. Not only is the handwriting bad, but the picture is a mess. There's so many colors on the screen. There's so much happening on that screen, isn't there? But from all of that, we were able to pull out some conclusions, right? Why do we bank turns? Go fast. To be safer. Right? Okay? So people can be safer. The banked turn means that they don't need as much friction between their tires, right? Okay? So when you go up to the mountains and you see that yellow sign that says 25 or 35, right? It gives you the turn, the arrow that's turning, right? And it gives a speed. How do they know that that's a good speed to be going in that turn? By the way, is that a speed limit sign? I'm not a lawyer or a peace officer, so don't take any of the following advice. Is that a speed limit sign? No. What color are speed limit signs? White with black lettering, right? Those are the legally posted speed limits. What color are the signs that are the recommended speed? They're yellow with black writing, okay? Those are recommended speeds, right? So you're like, all right. No, don't do that, right? How did they come up with those recommended speeds? Doing analysis, right? Okay. Now, unfortunately, a lot of our speed limits and recommended speeds were developed in the 50s and 60s when cars were heavier and brakes didn't work as well and the rubber of the tires wasn't as good. And so some states have not yet caught up with the modern equivalents of things. I'm not advocating fast driving because we know the faster the speed limits are, the deadlier the accidents are. that occur on those roads. So I'm sure there's other factors that go into determining speed limits and things like that. But as far as those recommended turn speeds, those are designed for safety, okay? Not to mention passenger comfort, okay? As the driver, it always feels way better than the person that's riding, okay? Because you have a steering wheel to hold on to, right? They've got nothing, right? So be mindful of your passengers. All right. Some of you asked me, well, how bad could it be, Mr. Balogh? There's your answer. Right there, okay? It can get bad. It can get bad. But I believe that this is like sort of peak badness. Between this and the connected objects with friction acting on them, right? You've got really the two templates, right? For how bad we'll make it for you in this class. That technically is me being done with chapter 6. So I'm ahead, which is good. I want to take a little bit of time here and let's give you a little bit of a boost on your homework. Chapter 5 was due last Saturday, right? Okay, so chapter 6 is coming up. And chapter 5 thrashed you, didn't it? Like, you're like, yeah, that's normal, okay? Let's do that one, okay? And let's go here. So let's give you a little bit of an orientation into what's going to happen to you in chapter 6. Some of you have already started on this, which is good. Most of you have not. Because why do today what you can do tomorrow? The answer is you need to learn something, so it takes time. We'll skip all the conceptual ones here. Let's get started right here, because I'll give you some time, right? I'll let you guys figure out the conceptual ones. All right. So you know what? I should be careful. You guys haven't done this yet, so let's do student view instead of giving you all the answers. There we go. All right. Questions. Okay. So that P right there, that is not the normal force, okay? There is also a normal force. Why is there a normal force? It's sitting on a surface, isn't it? It's like it's coming into contact with the surface. So there's going to be a normal force. They're just trying to say there's a force, right, that's pulling it to the right, and then there's like another force that's starting to lift it up a little bit, okay? Now, in this particular problem, you need to do a lot of what ifs. Because if that pulling force that's lifting this block up is lifting it too much, you're not going to have like static friction anymore. You'll end up with kinetic friction, okay? So the problem is going to ask you, like, you know, it's got these two parts for what P is, right? In this case, 10 and 12, right? Okay. They're telling you that it's not going to lift off the surface. If it lifted off the surface, what would the normal force be? 0. What would the friction be? 0. We can go home, right? But they're just saying that if you lift it up a little bit, maybe you've experienced this if you've been moving a heavy piece of furniture, right? If it's too hard to like push along the ground, you can kind of lift up a little. You don't have to like lift it completely off the floor and carry it. But if you just give it a little bit of a lift, it becomes easier to slide, okay? That's kind of what you're playing around here. So you're going to have to figure out, like, is static friction strong enough to keep this thing from sliding? So you're going to have to do some calculations to figure that out, right? Depending on the answer, yes or no, then you can determine what this force is going to be. Just remember that static friction can change its strength. It will always match its strength with whatever's going on to keep the surfaces from moving relative to each other, okay? But once kinetic friction's involved, it's basically a set thing, right? Which is why they gave us different coefficients for static, and can you see how the kinetic one is so much smaller than the static one? Okay. The static, that number right there in my problem, the 0.4, represents a maximum. That's the most that coefficient can be. But static friction's coefficient adjusts. It'll be anything from 0 to 0.4 in this problem, right? But once it tries to be more than that, it can't do it, and it'll revert to kinetic friction. I think you'll understand more about that as you start to attempt this problem, but it is going to take like lots of little calculations, what if scenarios, to see what's actually going on, and then you'll finally be able to answer the different parts. So this actually happens here in California, okay, in Death Valley, okay? These stones get pushed around by wind, but they get pushed around on the surface of a dry lake that when it gets water in it, okay, and because it's so salty, the buoyant force on the stone lifts them up, makes them just a little bit, and then the wind, like the rocks catch the wind and they start moving, right? So you go out one day and the rocks will be in one position, you come back the next day and they've moved, right? It's never aliens, okay? No matter what the History Channel tries to teach you, okay? It's never aliens. But yeah, you'll see the tracks that are left behind. And this problem is an easier problem than the last problem, right? It's like a more straightforward. You could probably start, like do this one first and then go back, right? To problem number 5. With this. I know there's a lot of words in here, but they're just telling you about the rocks, okay? But, right, they give you a coefficient, right? And they give you the mass, right? And it's really only one question in there. I have alluded to the penguin nightmares that you are going to have, right? For the rest of your life. You will never be able to see a penguin on the Nature Channel without remembering this problem, usually with a lot of tears and post-traumatic stress disorder associated with it. So penguins in a box, there is a force that's pulling the box up the slope, okay? And like problem number 5, the first one I showed you, you've got to do some what ifs, okay? If, like, for example, this force F up the slope is a lot bigger than the component of gravity pulling it down the slope, what direction would static friction be pointing? Remember, static wants to keep the box and the hill from moving relative to each other. And so if F here is a lot bigger than gravity pulling it down the slope, which way will static friction be pointing? Down the slope. Static friction will try to help gravity keep that force from pulling up. But what if this force is smaller than gravity? What if gravity's like winning and this force is not big enough? What's static friction going to do? It'll flip around to start helping it, right? Again, static friction wants to keep this surface from moving relative to each other, right? And what if we overcome static friction's ability to keep it still? Now we're in the kinetic regime, right? So this problem, again, you have to do some what ifs. I think there's like multiple parts. Yeah, A, B, and C, right? Okay. So they do this kind of interesting. Minimum magnitude of force that will prevent it from slipping. In order for this to be the smallest, which way would static friction be pointing? In order for this to be the smallest it could ever be, we want to keep it from moving, right? So we know the acceleration's 0, and we know gravity's pulling it down the slope. So we have gravity down the slope. How do we make this as small as possible? Which way would static friction have to point? Up the slope. Okay? Write down the equations. You'll see. You'll see it. Okay? And then for static friction, what is the maximum magnitude? Is that the second one? Minimum, to prevent the sled. What is the minimum magnitude that will start the sled moving up the plane, right? That's with friction the other way. And then what is the value required to move the sled at constant velocity? So what's the acceleration if it's moving at constant velocity? Still 0, but now it's moving. So what friction are we talking about? Good luck with penguins. Before you ask your question, I know this is kind of going fast, right? You're like drinking from a fire hose. So you may or may not remember anything I'm telling you right now, and it might be too fast to write it down. You don't have your homework notes with you or whatever. What are you going to do? Go to YouTube, right? We started this at about 8:45, right, into class. We haven't had any quizzes yet. So about 45 minutes into the video, you should be able to get to the part where you're going to, and then you just, as you're doing the homework problem, look up that problem, see what I said, figure out where I was wrong. I don't think I've been wrong yet, but it happens, right? Some of you write angry hate mails to me late at night. You told me wrong. I'm human, right? But yeah, right? So take advantage of that. Question? Keep it from not moving? Yes. Yeah, the question was, will static friction always go in a direction to keep the object from moving? Yes. That's kind of by definition, right? I put this question into the homework to remind you of the toolbox of kinematic equations, okay? So in this particular problem, you need to use Newton's second law, free body diagram, to find the acceleration of the car. And once you find the acceleration and you know a distance, how are you going to find out how fast it's going when the collision takes place? A chapter 2, one-dimensional problem, right? The dimension, the direction being down the slope, okay? So since no time has been given, you want to take a guess as to maybe which toolbox equation you might want to think about? Do you even remember the toolbox equations? No? Already got rid of them? They were superseded by by Newton's second law, right? That's a terrible pen. Delta x equals v naught t plus 1/2 at squared. And then v squared equals v naught squared plus 2a delta x. Which of those doesn't have any time in it? Third one. So I'm guessing third one. All right. Did we do a problem like this in class? Go see notes. Okay, so slight twist, right, on this problem. No angle in this one, right? But now we've got this extra block, the block C sitting on top of block A. Is there a normal force between C and A? Yes, okay. And we are given like coefficients of friction, right, between the table and all that kind of stuff. So think carefully about this one, right? Realize that whether or not A is going to slide is going to be determined by like combined masses of A and C, right? As far as the table is concerned, it really can't tell the difference between A and C, right? But C definitely is going to affect the normal force between A and the table. Roller coaster passing over the top of a circular hill. So in class, we did the hills. Where'd my black one go? It's all gone. We did a loop-de-loop. Okay? In this problem, the roller coaster car is going over the top of a hill. So it's a circular hill, so like circular in cross section. Is that too faint? You see it in the back? Okay. So the roller coaster car is going over the top of the hill. Which way is the centripetal acceleration? Towards the center. So what direction is towards the center in my drawing here? It's down, towards the center of the turn, right? Gravity is also acting down, isn't it? Which way is the normal force here? Up. It's between the surface of contact and, right? Because it's on the, going over this circular hill. When we did it in class, our roller coaster car was upside down, wasn't it? So our normal force is pointing down. This is a situation where we're going over the top, right, of a hill. Normal force will be pointing up. Okay. All right. Tension in that string, right, as that mass goes around on the top of that table, right? That tension will be determined by how fast it goes around, right? Faster that thing's moving, it's a circle. Don't let it throw you that it's horizontal on the tabletop, okay? Instead, your tension still, the centripetal force here, the force that's pointing towards the center, is the tension in the string, right? Hole in the table just changes the direction, and you can find the tension in the string if you know the mass of the hanging mass right there. But apply your centripetal acceleration, the v squared over r, right, for the acceleration. Do a careful analysis of what's keeping it in that circle, and you'll get it. Okay, so kind of a it's just variations on a theme. So when we did it together in class, our connected objects, one of them was like hanging off in space. In this case, you've got two that are sitting on surfaces, right? So both of these will have a normal force. Go at it. Draw your free body diagrams. Be careful of your directions. It's the same problem with a different coat of paint. Okay, and then this one, right? The banked turn. Now it says, the first part here, it's an unbanked curve. So based on everything we just did together, what angle are you going to put in? 0, right? We've already got the solution, right, for the unbanked turn, right? Wasn't it rug? Square root of rug, okay? So what magnitude of frictional force, blah, blah, blah. Go look at our things. If the coefficient of static friction, is it successful or not, right? Well, you can calculate the speed, right, and go for it. So a little bit more analysis. You might have to draw a free body diagram. You won't be able to like completely pluck that thing off the page, but it'll be really, really close. We've done the harder version, right? The banked turn. This is an unbanked version. I hope that was going to be helpful for you, right? Give you a little bit of orientation. Again, I encourage you to go back to the YouTube and listen to that portion as maybe you're doing your homework, okay? That sort of thing. Jershin, did you have a question? Oh. What is your friction if it's at rest? All right. The acceleration, if it's initially at rest, moving up or moving down. If it's initially at rest, what kind of friction are we talking about? Static. Is it changing its motion? No. So correct. Gravity's pulling it down, but there's a tension pulling it up. If there's remember there's static friction there also. There's 3 forces. Component of gravity pulling it down the hill, tension pulling it up, and then static friction is doing something. It's either up or down the slope. You have to kind of do some what ifs to. Yeah, net force on it has to be 0 because the acceleration is 0. Yep. Newton's laws, they're a bugger. Okay. Back to our regularly scheduled program. Yeah, I got some time. Let's do it. Let's get us started on chapter 7. I'll assume that you haven't studied any of this because who would? You still haven't done your chapter 6 homework yet. Did that. All right, did that. Back on track. So, all right. I'm not going to ask for a show of hands because I know what the answer would be. But how many of you just like really loved chapters 5 and 6. I'm not even going to look at you, right? Because chapters 5 and 6 are some of the worst things that could ever happen to a student at this point in their college career. Because it's a lot, isn't it? There's just a lot of analysis going on. Newton's second law isn't that hard, right? But it is. So if you had to, okay, so we can't blame Newton for much. He just described what the universe was doing anyway. But if we had to get down to like, what's really the difficult part about forces? What's that? Well, okay, the algebra is messy because of another thing. What is it about forces that causes problems? Starts with a V, ends with ector. It's a vector, right? I mean, would the algebra be easier if we didn't have to worry about x and y? If we just had f equals ma, right, with no having to deal with directions, it'd be a lot easier, wouldn't it? Okay. So what chapter 7 and 8 are is your first introduction to conservation of energy. And what is energy? Energy is a physicist's way of working with forces without having to work with vectors. If we could just get rid of the vectors, life would be easier. I say all that. Now, of course, we can't completely get rid of vectors. Directional things in the universe are very important. However, energy is a way to be able to work with things that have direction without having to do all the vector math. And so that's why conservation of energy, sometimes students come up to me, Mr. Balogh, this is so much better than Newton's laws. Why didn't you start with this? Fair point, okay? But I guess at this point, if we had started with conservation of energy back in week 1, everybody would have dropped the class, right? You'd be like, I'm out, okay? There's a reason we start with kinematics. Kinematics tends to be very straightforward, very algorithmic. We then throw you under the bus with Newton's laws, where there's hardly any algorithm, right? You have to know like how to use the skills of a free body diagram and apply Newton's laws, and that's why it's hard. You want an algorithm. You just want like, just give me the equation and I'll solve it, right? Well, that's just math. That's just algorithms, right? We're asking you to be better than that. We're asking you to think and apply the information that you're doing. Conservation of energy is a little bit of a return to that sort of algorithmic step-by-step way of doing things. We pay a couple prices, but by and large, those prices are easy to pay. Do you remember our discussion about what is mass? And how it's so hard really to kind of define what it is because it's something we experience, something we can measure, but we don't have the words. Energy is a little bit the same way. And I first heard this from Paul Hewitt out at the City College of San Francisco, and it stuck with me ever since I heard it, right? As I think really kind of the best verbal description of mass and energy. You know enough, you've been alive long enough, and Einstein has been dead long enough. You know that E equals mc squared, right? That energy and mass somehow have an equivalence. They're like two sides of the same coin. But I think Paul Hewitt really kind of gets to the core conceptually of what's going on here, right? And so I can ask, like, I can't really ask you what is energy. You'll struggle, right, with like what it is. But if I ask you to name types of energy, let's do that exercise. What kinds of energy are there that you know about? Kinetic, solar, potential, wind, chemical, mechanical, nuclear, electrical. Like these are all forms of energy, right? We pay PG&E or we pay SoCal Edison a certain amount of money so that our homes can be supplied with energy. Right? We use energy. We put gasoline in our cars. We put chemical energy into the gas tank to turn it into mechanical energy so we can zoom, zoom, go places, right? So energy seems to be this thing that allows us to push stuff around, right? Whether we're pushing mass or we're pushing electrons or whatever's going on, right? We're getting energy to do our bidding, right? We're trying to focus it, we're trying to collect it, we're trying to do something with it. And so that's what we're going to do for chapters 7 and 8. We're going to try and tackle this concept of energy narrowly at first to apply to just forms of what we call mechanical energy. Electrical energy, that's physics 4b. Okay? Not going to talk about that in physics 4a. Nuclear energy and chemical energy, that's really not going to happen until physics 4c, because you need to have some quantum mechanics and nuclear physics under your belt before we can start doing that. So in the 4a series, we are going to talk about mechanical energy, namely kinetic and potential energy, the potential energy associated with position, like where things are, okay? Or like in a spring or a rubber band, like what's stored in the stretch or compression. We call those forms of mechanical energy because they're unique from, say, the energy that exists because chemical bonds exist. That would be chemical energy. Nuclear energy would be the energy that's contained in the nucleus of an atom, in the forces that are holding the protons together. So those will come later in your physics career if you have to take those classes. By show of hands, how many of you have heard of conservation of energy? Yeah, this is a very common thing, right? And to conserve something in physics means what? That we're all good little hippies and we turn the lights off when we leave the room? I'm a good little hippie. I'm always turning lights off and things. What does it mean to conserve something in the physics sense of the word? I know you've heard it before. It's not as, we kind of tend to go towards our modern sophisticated understanding of we should be conserving and using less of it and being more efficient. But that's not what it means in the scientific sense. Your eyes are going to all light up. You can't make it and you can't destroy it. For something to be conserved in a scientific sense, it means that there is a set amount of it. We can't make more. We can't get rid of it. What we can do is change it from one form to another. And so we're going to be keeping track of energy changing its forms. And the two main forms we're going to deal with are kinetic energy, the energy of motion, and then potential energy, the energy of state, like location, what's stored in that thing. But overall, we really can't make any energy. So if we've got solar panels on the roof of the building, are we making energy at the solar panel? No, where are we getting it from? The sun. We can't make gasoline. We can dig up the old dinosaurs and trees. It's not really dinosaurs, it's mostly trees. And refine the petroleum product to make it something that is more condensed in its energy content, right? But we can't really make it. Where did the energy come from? No. Ultimately. The trees. Where did the trees get the energy? Okay, right? We can harness the energy of the wind. But where does the energy come from to move air around? You've said it twice already. The sun. Okay? It kind of always comes back to the sun, doesn't it? Okay? And that's true for any burning of a fossil fuel or solar panel or wind. You have wave energy, which we could probably blame on the moon more than we could blame on the sun. And then nuclear arguably didn't come from the sun. the nuclear energy we have on the surface of planet Earth came when the Earth formed at the same time the sun formed, which I guess would go back to the Big Bang. But the universe started with a set amount of energy and will have that amount of energy for forever. There is no energy crisis. I want it to be very clear here. There is a crisis, but it's not one of energy. It gets me really mad when people run around and say there's an energy crisis. We are not running out of energy. What's the problem? What's the crisis? Specific types we may be running out of, but even that's not really true anymore. When I grew up, they were telling us that we were going to run out of fossil fuels by the year 2000. I'm a child of the 70s and 80s, right? Coming of age in the late 80s. And I was being told that the year 2000, there was going to be no more gas. Well, guess what? We haven't run out. And we probably won't for another 300 to 400 years. And that's just the known deposits of fossil fuels, right? They're still discovering things. That's not the problem. What's the problem? The stuff that's easy for us to use, the stuff that we can go out and get at the gas pumps, is destroying our climate. It's making our planet unlivable in places, right? And so that's the problem, right, that we have to solve. It's an entropy crisis. It's not an energy crisis, but people don't like to hear that either. All right, so in trying to solve this problem, okay, I'm going to give you the punchline. This is something your book's going to wait until next chapter to give you, and I can never figure out why. Okay? But one way to sort of say this, right, is that whatever energy we start with has to be the amount of energy we end with. And if you've taken like high school physics or anything, this is probably what they talked about, conservation of energy. And then you do what you start with, you do what you end with, set them equal to each other, solve for the thing you don't know. This actually is an oversimplified way of talking about it, because there's another idea that we need to talk about, because I can break this very simple form of conservation of energy really quick. Here we go. You're sitting in your car at the stoplight. It's red light, turns green. If you are not moving, what is your kinetic energy? Zero. Kinetic means motion, right? If you're not moving, you have no kinetic energy. And then you hit the gas and you start moving. Is your kinetic energy zero anymore? No. You started with how much energy? Zero. And now you have energy. What happened? We just broke the conservation laws of the universe. Universe.exe has stopped working. Press OK. Something happened. We burned chemical energy, right? But a lot of times, we're not going to deal with like all those things that chemical energy is, or all those things that nuclear energy is, or solar energy is. There's a different way of writing this down. And this is how we're going to use it in this class, okay? There's going to be this thing called work. And that right there is W for work, sub other, okay? Plus the initial energy I have equals the final energy I have. So in our car example, okay, we know that we started with zero kinetic energy, but we ended up with some final kinetic energy, the energy of motion. Where did it come from? It came from the work other, namely the systems of the car that changed the kinetic energy of your car, right? It's a black box. Work other is like this universal recycle bin. We'll toss anything that we don't know how to handle. Gasoline, nuclear power, solar power, electrical power, all these things that we haven't taught you yet. We're going to throw them in the recycle bin of work other. And that will help us to solve conservation of energy problems that are more sophisticated than just starting with and ending with something, because I can start and end with 0 all day long. So that is the idea. So what we're going to do when we get together next time, and what you should focus on in your studies in preparation for Thursday, work. We're going to talk all about work next time. Really intense on work and this focus on work. And then we're going to get into kinetic energy. Next week, we'll talk about potential energy, and then we'll bring it all back together and solve all the problems we've already solved already, but do it from the point of view of energy. I'll see you tomorrow. Lab number 5. Be ready.